initiate my screen sharing and start leading through review of some of the material. So, as noted, we're talking about cellular sheaves on simplicial complexes. And I think everyone here will recall a notion of an abstract simplicial complex. So here we have some set of vertices, and each element of the abstract simplicial complex can be treated as kind of having a non-empty ordered set of these elements. And that itself is called the simplex. So, for example, the vertices here are V1 through V7. And each of those vertices are in here, but so are a variety of higher dimensional structures, higher than 0 dimension. Those are the 0 simplices. But then we have one simplices like V1, V2 for this edge, for V2, V3. And we have 2 simplices as well. Beyond those edges, there's 1 simplices. Beyond the vertices, 0 simplices. We have 1, 2 simplex here, which is this triangle, V4, V5, V6. And we name each of them by an ordered list, or some people call it an ordered set of the vertices that make it up. And a key property here is that this is closed, so that if a given simplex is in our collection, and there's a non-empty set of vertices that are a subset of that, then that non-empty set is itself associated with a simplex. So, for example, this is closed under taking subsets of things. So the fact that we have V4, V5, V6 here guarantees that in order for it to be a legitimate abstract simplicial complex, V4, V5 also has to be in this. So it's a subset of the vertices of V4, V5, V6. So if we consider V4, V5, that has to be part of it. And indeed, here it is. Same thing with V5, V6. That also has to be a simplex here. Moreover, if we go down 2 dimensions, V4 has to be a simplex, right? And so on. So we have this characteristic of closure. All the vertices themselves have to be in this, but we can have these higher dimensional simplices, but all subsets of them, so to speak, have to be in it as well. And I want to draw your attention to the fact that vertices are 0 simplexes, edges are 1 simplexes, even though they are 2 vertices to make them up. Even though a vertex is 1 vertex to make it up, it's called a 0 simplex because it's of that dimension. This is of 0 dimension. This is of 1 dimension. It's like a linear thing. This is of 2 dimension. I think all of you remember this, right? So this would be familiar. And you may recall that prior to reading week, we talked about taking these abstract simplicial complexes, like this one that features prominently in this chapter, and drawing associated with them the poset, the partially ordered set, or if it were pre-order also, associated with the underlying simplicial complex. So just as we could draw this out in a pre-order, this abstract simplicial complex, we do that here. So, for example, we have 1, 2 simplex, C, D, E, and that's up here. And attached to that is, for example, simplex CD, right? And simplex CE, CE, and simplex DE, right? And attached to them, for example, are Simplex E itself is attached to CE, and it's attached to DE. And simplex F over here is also attached to EF here. And we will write, and this is rather important for some subsequent slides, we will write an attachment relation, the fact that D is attached to AD, and here we go to AD. We will write that with a little squiggle. And I think Jeff identified some missing lines here. Is that right? Yes. Oh, maybe we remedied them? Okay, this one here, maybe?
There was a couple that were pointing up to the right.
Yeah, okay. So always valuable, so thank you. Okay, so we have these relations, and I want to convey this. This is a drawing of this as a traditional poset. This drawing is the same information. We happen to omit the empty set because it always points to all the vertices, and by extension, by composition, everything else. But I hope you recognize that this information is the same as this one. It's just that this is drawn in a geometrically, in a way that its geometry mimics this. Do you see that? Right? And the point is this edge AD here is explicitly called out for being edge AD, and there's attachment relations explicitly shown that are only implicit here. Are we comfortable with this? So this is going to be the poset as well. This is a drawing of the poset. We just don't arrange it by height in the poset like we do up here, right? This is kind of by sort of its one thing greater than another. CDE is greater than CD, greater than D, right? In our language of our poset. Here, we don't really draw it in that geometric way, but it's the same information. Are we comfortable with that? Yes.
So, remember, the simplicial complex also have orientation, right? Like clockwise or counterclockwise.
Correct, and we're going to be getting to that a lot next time. Yeah,
it will determine the cohomology.
Exactly. Yeah, we're going to be discussing that centrally next time.
Like the slide, you should mention that it's a clockwise.
Clockwise, in terms of the labeling. Yeah, that's a good point. We're going to be explicitly having to worry about those orientations next time. Right now, yeah, anyway, we'll come back to that. It's a very good point. Okay, you folks will remember that these abstract simplicial complexes can be lent topologies by this construction of the Alexandrov topology. And because this is review, I'll just remind us that we build up this topology, we generate this topology by taking each simplex and that includes not just the zero simplices, the vertices, but the higher simplices like edges and face this two simplex, for example. And we take over each of them what's called the star of it. And the star gives, for a given simplex, a set. And that set consists of, as its elements, all simplices that include the simplex with which you've started. So let's take simplex V1. This has as its star V1 itself, because it's included by itself, but also V1, V2, right? Because it's part of that. V1, V3, because it's part of that. V1, V5, because it's part of that, right? And I think you'll remember this for V3 as well. You can just see it, mutatis mutandis. But this holds true for higher dimensional simplices too, or simplices of dimension more than 0. So take this one simplex, V1, V3. The only simplex that makes it up is V1, V3. Can you point out to me any one simplices, any edges whose star includes something of higher dimension yet? There are some edges here that are included, whose star includes some higher dimensional simplices.
V4.
Yeah, well, okay, so I'm looking for an edge, so V4,
V4, V5.
V4, V5, that's right. V4, V5, should, oh my gosh. Okay, V4, V5 should include V4, V5, but it should also include what? V6, yeah, exactly. So that should have been present. So Jeff spots another error.
No, you spotted it.
Yeah, yeah, great. So because it's part of this higher simplex, it should be V4, V5, and V4, V5, V6. Are we clear about that? And same thing for V5, V6, and the same thing for V4, V6. Are we good with that? Okay, so the idea is that each simplex, we take its star, and then we take the union of all those stars, and we get a topology. And I've noted before that this reflects the fact that if we take the intersection of any of these, it's going to be the star of another one. So it happens that, if we take the intersection, for example, of this V1, V3, and we take an intersection, the star of V1, V3, or V3, V1, and the star of V1, we get V3, V1, which is indeed the star, the star itself, right? If we take an intersection of V1, the star of V1, V5, and somewhere we should have the star of V1, V5, which includes V1, V5, as well as V4, V5, V6. Right? Excuse me, no, that's not true. It's just V1, V5. We take the intersection of that with the star of this, for example, we'll get V5 alone, because the star of this entire complex here, V4, V5, V6, which should have, that should be written down here, is just itself. And if we take that, the intersection of that with V1, V5, we will get V5. That's its point of intersection. So the intersections of these things, you could think of them as kind of rising up from here. So for example, the star of C here is going to include all the things above C, right? So we could have drawn that out as kind of a blob up here, and includes this thing here, right? And this thing. And if we take the intersection with any other blob from an upper thing, say from B, well, let's look for something more interesting. Say from a blob up from it, there'll be an intersection between them and like AC. So it's kind of like an intersection of a cone, right? One cone with another. It'll be itself rooted at some place. And Jeff gave the analogy of a tree. It's like a tree rising up out of each one, and there's some intersection that itself is a tree. Remember this? Okay. So these, well, this is somewhat hand wavy, these have the features of a topology. And share the feature of the topology. The entire set is in there as the union of all of them. There's an empty set in there as the union of two disjoint ones, etc. It turns out it's a topology. So that's by way of review. One further thing that we had indicated was that, and I think this is rather late in last session, that the Alexandrov topology, when we consider computing the Alexandrov topology for a poset, there's a contravariance involved. And so if we have this poset and we consider the star for C, for example, we'll get this blob above C, right? All things above it in this poset, right? So it'll include a C, B, C, C, D, C, D, E, C, E, and that's a certain set. But if we consider something above it in the poset, CD, that star will be related to the star for the thing below. So if we consider CD, it's the star for that is, so CD is above C, but the star for CD is included in the star for C. So in some sense, if we think about a category of set and relations, if CD is above C in the poset here, the attachment poset, the star for CD will be less than or equal to the star for C in the category of sets and inclusions. It's like, but when I say less than, the star for this will be a subset of this, right? So it's kind of less and that, right? So if we have an attachment, and remember this depicts attachments, right? C is attached to CD. So if we have an attachment, A is attached to B, then we have the relation that star of B is less than, is subset of star of A. We good with that? And recall that the Alexandrov topology is based on this. Each thing is mapped to its star. And so the Alexandrov topology is in fact associated with a functor from this category associated with the poset category for our attachments, to a category given by sets and inclusions, right? The O of P, the topology opens category, where we have the objects as these sets given by stars of some object here, so set for C, set for CD. But in this one, so in this original poset for the attachment, CD is greater than or equal to C. But in this one over here, the set for CD will be less than or equal to, that is a subset of the set for C, right? And of course, the morphisms here in this category are these relations, these less than or equal to. Remember, it's not a function, it's not a map in a traditional sense, it's a relation, right? This is a relation. This is the morphism here. C is less than or equal to CD. And that leads to, if we call this contravariant functor F, it leads to F of C. So C less than or equal to D over here means that F of CD is less than F of C over here. It goes in the opposite direction. It reverses it, right? Are we good with this? We good with that? Okay. Okay, now you gotta bring it home, the sheaves. You gotta bring this thing home. Okay. So you'll recall with sheaves in this classroom, not 3 weeks then. So we discussed how sheaves can be taken as mapping from, in a contravariant way, from a category associated with the opens of some topology. That's this, right? This is some topology. We have and we have some, this is associated with a cover U, this fragment of the topology associated with this cover U. And we had this functor, which maps from that over into set. So it maps U to F of U, F of U1, or sorry, U1 to F of U1, but it does so in a contravariant way, right? Remember what these morphisms here over on the left, what do these represent? What is a morphism in this? Is there inclusions? This, like this region is included in that, right? That turns over here, it's mapped to a morphism over in set. And what's a morphism in set? It's the category of sets and begins with an F. Functions. This is a function going down. This is what we called a restriction map. Do you remember that? Maybe it's a bit rusty, but do you remember that? So we had inclusions here, mapping over into restrictions here. Do you remember that? So that if in our sheaf situation, we had data on one region or one region included in another, it's a subset of another region. This would mean if we had data over the entire region, a bigger region, we could restrict it to us data about this, right? Or if we knew here that which functions are continuous over this bigger time period, we could by per forte, we could recognize that those functions must be continuous over the smaller time interval. So here it's sort of saying, okay, it's actually a monomorphism of this into this. Yeah. And you may remember, and this is important, all of these things have to commute. So for this to be a sheaf, we need all of these, just as these all commute, because it's a poset, all of these commute here. All of these have to commute. We have to have a consistent picture for this up here, given by all of these different sets out here. If we have parts of U that are mapped down through U2 to a small area of U1 intersect U2, two different ways, through U1 and through U2, we have to have the same, we have to ascribe the same information for that small subset, regardless whether we consider it as a subset of U2 or of U1, right? Okay. Okay. So it turns out that this is from up, because this is inclusion going up here. This is restriction going down. Remember that? Remember that? Reversed it. But remember this contravariant functor, the fact that this is a contravariant functor from this poset, it's contravariant to the topology. The stars for these are smaller than the stars for these. Remember that? Well, that means that if you compose these things, there's a functor from, think of it, P to O of X. We could call it, if you want to call this X, to O of X op, and then on to set. There's actually a direct functor here from what's called the face poset, this sort of thing, directly over into set here for the sheaf. So here we go. A cellular sheaf on a cell complex, one of these cell complexes with its face poset like this, consists of an assignment of data for each cell, each simplex of that. So we have a piece of data for for this guy, this guy, this guy, this guy. But notice, and this is extremely important, we have data for the edges too, AD. Mhm. We have data for, so it's best to think of it as like having data for this, for this, for this, for this, for this. In other words, not just for these vertices, but these higher dimensional structures as well. CDE has data for it, right? Are we good with that idea? So we're going to have data assigned to each of those, but that's not going to be it. For each attachment morphism, so each attachment here, remember, oh, I had a nice thing of showing it, but each attachment morphism, just like that, we're going to have a map on data for this to data for that. For the thing, whence it comes to whither it goes. It's going to have a way of translating data on D into data on the edge, this higher dimensional structure. So I said there's data for each of these structures, not just the vertices, but the edges between them. But more than that, these morphisms, which are morphisms in our face poset category, they're these morphisms here, right? Those are morphisms in our face poset. This is a category, this is our face poset category. They're morphisms here. Each of those morphisms turns into a morphism for our sheaf, which you could think of it as a co-restriction morphism or an extension morphism. It translates data for the lower dimensional thing. Notice this is lower dimensional. This is this simplex here. This is it's a simplex, but it's a vertex. It translates data from the vertex into data for the higher dimensional structure, the edge, right? This morphism here translates data from the edge DE into data for CDE. So what I'm saying is that there's data for each of these assigned by a sheaf. There's a stock of possible values and a given assignment of data where they have a particular value from that stock assigned here. And then this will relate the data here to the data here. It will say what mappings are consistent here from this to this. And in the end, if we have a consistent data assigned to all of these, this will have to show that the data that's assigned here is compatible with is what would be mapped to from the data here. So that's where we're going. And let's look at that here. So it's saying for each attachment, lower dimensional simplex to a higher dimensional simplex, a morphism would be in the sheaf category, in this kind of co-restriction morphism. It's going to be relating data from the lower dimensional structure, think vertex, for example, to the higher dimensional structure, think edge, for example. Or this could be edge and to simplex, for example. Okay. Yes, there are two questions. Yes.
My understanding the morphism from F tau to F sigma to F tau, the linear transformation is restriction map, not the extension map.
Well, okay, so this is let me think if that is it is, you could call it a restriction map. Okay. It's just it has a different feel to it than for a situation where, yes, I would call it a restriction map. I think that's a fair comment. I think I may have heard it called a co-restriction map, but that would be for co-sheaves, actually. So you're right. Here it's a restriction map. And I guess you could say that it's a restriction, because D might represent the situation for one municipality, and AD might represent an area of overlap for municipality A and municipality D. So yeah, I think that's a fair thing. You're right. That I should have called it a restriction map, not a co-restriction. It's for someone who's coming at this from topology background, it may seem a bit weird because there we think about kind of something that's broader, narrowing down to something that's narrow. And you might think, well, like we have a one simplex narrowed down to a zero simplex. That should be called restriction. But no, actually, this is the restriction map. Because there's this Alexandrov topology, the star for this is actually bigger than the star for that. So it's restricting down from the stars. And as I say, often these higher dimensional things might represent like a smaller area of space than either one of these. So these might be things applying the entirety of this jurisdiction, the entirety of this jurisdiction, and this higher dimensional simplex represents things present in all three. So yeah, I think that's a fair thing to say. It's a restriction. Yeah, it's a restriction map. So that's good. It requires you to remember that even though it seems like an edge is broader than a vertex, we're actually going from the vertex, which is a big star, and narrowing it down to a smaller star for the edge. But the point is, one of the points here is that you don't actually have to worry about the Alexandrov topology that much when you built these things, because there's actually a direct functor from this post set. I'm just gonna go copy this and put it there so I don't have to keep on going back. So there's actually a direct functor here from this to this. We're not dealing with the stars explicitly. We're not having to build up this topology. We're actually having a mapping from a cell complex for each cell is the points of analysis here. And we can look at essentially attachments here. Now, we could write, if we think about the data assigned to tau, so here we have, maybe we call this tau, this sigma, right? This is sigma, this is tau. We have an attachment of sigma to tau. So sigma, this is tau, right? Attachment there. Then we have a map from data for this to data for that. Are we comfortable with that, with the sheaf? Well, so this relates possible values here to possible values here, relates each element of the stock here to each element of the stock here. Possible values that could be assigned to sigma to possible values that could be assigned to delta. Are we good with that? Well, then if we could think about a particular value assigned to tau, particular value assigned to the higher dimensional thing. So this thing here, possible value assigned to it, that is equal to some map for this map here, mapping from a value for this to that equal to this. So whatever value we assign to this, if we translate it into a value for tau, we have to get the value for tau. Now, you'll notice that I, following Rosiak, have written this in a very suggestive way, because what he addresses in what's an extremely common treatment of this is that the target category F goes between the face poset of the cell complex X from this poset, a category for this, into a category D. Commonly, that's associated with a vector space. Okay, treat it as a vector space. And here, what we've written is if this is a matrix, a linear transformation, this is a vector of data over sigma. So a vector of data here, and we translate it into a vector here. So maybe there's a 4-dimensional vector here, maybe. Maybe there's a 2-dimensional vector here. And this is a 2x4 matrix. So we multiply this 2x4 matrix by this 4-dimensional vector for this, and we get a 2-dimensional vector out. So the point is, this F sigma to tau, if we're dealing with vector spaces, it performs this mapping. Right, it's this operator that if we multiply it by the value for sigma, we'll get the value for tau. Are we okay with that notion? Okay, so and maybe I should say, and I should have probably included this back there, that we're dealing here with a category which Daniel Rosiak mentions in the book several times, this category vect. And we should probably just make sure everyone's on board with this. The objects of the category are vector spaces. And the morphisms are linear maps from one vector space to another. Now, this may initially seem disorienting, but I just want to remind us of the category set. The objects are sets, right? The morphisms are functions between sets. The objects there have elements, right? They have points within them that we call elements. And they're mapped from one set to another in set, right? There's no structure there. There's no one element is bigger than another within a set. They're all at the same level. They're all just jumbled together, right? The points within the set. Here, we have objects that have more structure. We have vector spaces. We can think of these points within them as being like particular vectors in the vector space, right? Particular vector in a vector space. And the morphisms we could think of as being associated with linear operators, like you might think of it as a matrix in many cases. It multiplies one vector from one vector space and turns into a vector in another, right? So we might have, again, a vector of dimension 4. And so that's just like in category set, we might have an element of a set. That's a point in some vector space, in some object, right? And we have a morphism that represents this linear transformation, like multiplying that times some matrix, say a 2x4 matrix, 2 down, 4 over. And that turns it into a 2-vector in another space. That's a morphism going from the vector space of dimension 4 to a vector space of dimension 2. It's a morphism. It maps each. You'll forgive me if I say each element of or each point in that original vector space of size 4, each little vector, it's mapped into a vector in our vector space of size 2, of rank 2, of dimension 2. Are we okay with that notion? So what I'm saying is that's what's going on here, that here F of sigma might be a vector space with dimension 4. This is a vector space with dimension 2. And we carry out this mapping through a matrix multiplication. Are we good with that idea? This is going to be very common in the sheaf, and particularly cellular sheaf area. Fact. Okay. Now, I want to make sure we're all on board with with what's going on here, because there's several different levels. We're talking about stars and Alexandrov topologies and cell complexes and simplices and vertices. And I know it's easy for the mind to spin about all these. I just want to make sure we're all on board with this. So we have a simplex in our diagram, right? What are these simplices? Okay. A simplex is going to be this edge here between D and AD. Are we okay with that? And we can then unpack this into an attachment diagram, right? So I'm sorry. I said this is our simplex, AD. We can then draw it out as a little cospan here in our attachment diagram, right? Right? Here's our little attachment diagram fragment, which has that in there. That represents, are we all okay with that? That represents this. This edge here, AD, remember, it's a thing in and of itself. This is not just depicting a bunch of vertices. This is a thing of itself, just like we have a two simplex, CDE. That's a thing in and of itself. These edges are important things. They are structures. Do you see them? This one here? So this has this attachment diagram that explicitly calls out that we have something called AD. It's a thing. It's reified. It's a thing. We okay with this? So we have this attachment diagram, right? Now, when we map this over with our functor from this poset category, from this poset, we hit it with our functor. That turns into each of these is an object in that category. Each of these is a simplex of this category, right? In this poset, right? Each of them is an object here in this category. So we hit each of them with F, and that gives us a stalk over each of them, possible values. Maybe they're possible, it's associated with a vector space, which tells us possible vectors in that vector space, right? But then these morphisms in this poset category, those morphisms turn into morphisms here, right? Which are, if these are vectors, these are linear maps. These are matrices, right? That's why we get this thing. It's like a matrix multiplication going from this to this. Going from this vector space to this, from the vector space assigned to this to the vector space assigned to that. The vector space assigned to this to the vector space assigned to that. Are we comfortable with that? We good with that idea? Now, but more than this, and this is where the sheaf property holds. Remember this idea here? All these paths have to commute. Remember that? All of these different ways have to agree with what's going on here. All these different ways. If you have data up here in U that's in some subset of some, U1 intersect U2, it has to, the assignments that we make to U2 and to U1 have to agree about this, right? Okay. So what I'm saying is that whatever value, specific value XA we assign to A, whatever specific value we assign to D, they have to give the same specific value we assign to AD for it to be a sheaf. They have to play together nicely. If they have to be consistent, coherent, they have to all give the same picture for AD. And that means that if we take the value for A and we hit it with this mapping, F of A attached to AD, you could think of this as like a matrix multiplication. We need to get the same value for AD than if we came down this other area, right? if we came this way. If we came this way, we have a value for x. For d, I'm calling it xd, you could think of it as like a vector. But we multiply it by this. You can think of it by a matrix multiplication. We're going to get a value for AD. Those two have to agree. Those two have to agree. It's just like saying these have to agree if we come these two different areas. They have to agree on their overlap. You could think of this as kind of they have to agree on their overlap. Whatever we believe is going on for all of A, whatever we believe is going on for all of D, they have to agree for the areas for what they apply about common places into both, for example, or things that are associated with both. Are we okay with that? Yes. Mehdi.
Vector space, the dimension of the vector space for each A is bigger than its A.
So the dimension for a vector space for XA will commonly be bigger than this. Yeah. Because you may have more information about things here, for example, than you do about things here. Or there may be more possibilities. Maybe you have a lot more sensors in place, a lot more measures in place here than you do here. So that's why I was saying, for example, this might be a vector space of dimension 4. This might be a vector space of dimension 2. Because these are the small subset that are just in that region of common overlap or what have you. And this will take that bigger information down and plot it down to what it would imply about those two. And this may be a vector space of size 4, for example, but it could be a vector space 3, for example, or 7. Like there's nothing that says that f of d has to be the same dimension as this. We could have very different data on each of these places. This might be a city where we have wastewater data. This might be a city, in addition to public health measures. Maybe in this one, they do extra good contact tracing and they do some screening studies, so we have data there. And basically, we can have different data assigned to these, and what they depict for this common area needs to be shared in common as translated through these maps. Like these maps are going to take this and say, okay, what would it imply about this common area here? This common area between them is the idea. Does that help at all? Are we like any questions about this? Any questions about this? Yes.
Sheet over cells is not a contrariant pointer.
It's not contrarian. No, it's covariant. That's the interesting thing. And so it goes from, and well, we're going to get to that in just a minute with a little example here. It's a cellular sheaf is a covariant functor from the face poset. Now, I'm a little bit confused about the notation used at different places in Rosiek, but here the face poset, this face poset, is being denoted. Where am I? Is being denoted with the f of x. So if we have x, here's our x, right? Remember here, don't get distracted just by the vertices. We also have AD and we have CDE and stuff like that, right? This is our face poset category down here. It happens to be drawn geometrically like this, but it's a poset. These are sort of order relations. And this is a covariant functor, Mehdi, because we have this op relationship with the topology involving the stars, and then we have this op here. You compose them and you end up getting a map directly from this face poset category, like that goes, if we have data over this and data over that, we have this mapping between them that's covariant. We have a map from this to that we for this morphism here,
And
this attachment morphism, which is what we were talking about here. Yeah.
I can see that a composition of these pointers, one of them is contravariant and another is covariant. The composition of them is contravariant.
Well, this is contravariant in its own way, right? This is a contravariant functor here, and this is contravariant here, right? So you have so this is something where I would really need to check the notation. I think of this as the face poset for poset P, the face poset f of x here, and this is associated with O of f of x, the topology for that, and it's from this topology that we map here. So I believe what it boils down to is you have this composition of this contrariant functor with this one, and that forms a net covariant functor in here. The book talks about this a fair bit using wording that's a little bit, I mean, the implication seems to be fully the same. They explain it a little bit differently, but the net result is unquestionably that this is a covariant. A cellular sheaf is associated with a covariant map from the face poset to D. And the amazing thing is you don't need to worry to some category D. You don't need to worry in your head about stars and Alexandrov topology and what's bigger than what and inclusions. You just work in terms of these attachments here in this, and these as your objects. And you don't have to get involved in building up a topology in your head because you just have this direct map between them, which is rather pleasing. And I was trying to sort of unpack what that means here, but essentially that gives us this covariant relation. Now, mind you, there's a co-sheaf, and Ujia was right to say, like, this is really where the co-restriction maps come in. The extension maps come in. And cellular co-sheaves are really valuable too. So don't get me wrong. It's not like cellular sheaves are somehow the important thing. We just have covariates for co-sheaves here. We have for sheaves, we have contravariants for co-sheaves, covariants for sheaves. I don't know if is that helpful, Meti?
Yeah.
Okay. And again, a lot of the time D is taken to be vectors. This is true for the work like with deep learning, the application with Daniel Gebhardt, but it's also quite a bit of true with some Justin Curry's work, et cetera. I think that we have vect. And there's some reasons for this. We can go through a categorification and decategorification process and actually try to pack in. And so this is a little bit of an aside, but see this category D here? If we have a category D that's not vect, if we have a category D that involves some other structure that we want to capture, maybe it's something as mathematical as group structure, maybe it's something involving C-sets or what have you. The way that most, certainly I've seen I've seen Robinson take this approach, and my impression is that it's applied by Grist and others as well, is that you basically decategorify this into vect. So you basically use a vector space to encode the categorical structure. Now, as we'll see from our first paper involving Leal, Bumpus, Fairbanks, and maybe Cafaro as well. I think he's a co-author. we can actually, in something like CATLAB, in categorical computing, we can work with a D directly. We don't have to decategorify it into vector.
Yeah, because D generally speaking is a billion category.
That's right.
That's why we can apply the algebraic operations, for example, the linear operations.
Right. That's exactly right. That's exactly right. So you can actually unpack it into vect and sort of use vect to, I mean, what this gives you with D is it gives you types, extra typing. Like you can give typing, but you can unpack that into vect and use different dimensions for different types of things.
So that we can calculate, for example, kernel for.
That's right. Exactly.
For
Yes. Yes, that's exactly right. That's right. Okay. But one thing you could do is you could work with equalizers and co-equalizers with arbitrary categories. And that's what John does in that paper with Aditya Chaudhary. Okay. So what we have is a picture like this, and I'm using diagrams from the book. So this is our simplicial complex, right? And again, don't be only distracted by the fact that only vertices are labeled. There's higher dimensional vertices. There's higher dimensional simplices here, like AD, AC, that are just as real as any of the vertices, right? Those are higher dimensional simplices. It's CD, DE. I'm calling higher dimension, including one. Okay. So I think we're all comfortable turning this into this poset, right? This shows attachments, right? We good with that? So CDE is this thing. And what we have here is, for our sheaf, it's a functor here. But Meti, this is not just covariant. This is actually a functor that basically you don't need any, I believe you don't need any extra structure on this functor. This is just a functor from this, for example, into vect. It automatically carries enough information here that it will guarantee a single global section that's unique if you have this matching up of different properties, which is really powerful. It spares you worry about proving whether it's a sheaf. Okay. So what I'm saying is that here, and this is beautifully illustrated by Rosiak, each of these simplices is translated over into its associated stock. So this D, this is F of D, right? This is BD, this is F of BD. This is CDE, it's translated into F of CDE. So F of CDE is some vector space of a certain dimension, here just dimension 1. D is translated vector space of dimension 1. Maybe CD is translated vector space of dimension 2. This is the result of mapping it over. And what's important, though, is not just that it doesn't just map these over, each of these simplices, it maps the attachments between them. Remember, we saw that here, right? It maps the attachments, right? Between them. Maybe I'll, again, copy that here in case I want to switch back to it. So, oops. Why did I not copy the right one? This is the one I wanted to copy. Oh, I see. Duplicate it. Okay. Here. So you remember that we have these attachments between A and AD. Those get mapped into some morphism within our space. So this is an attachment, D to AD. It gets mapped over to some mapping between those vector spaces, right? This one here, CD to CDE, gets turned over to a mapping between those vector spaces. And as you can see from these illustrations, these are matrices, because here we're mapping it into vector spaces and these are matrices. So if we know something, if we have some value drawn from the reals here for D, we can translate it into value drawn from pairs of reals by multiplying it by a certain vector here. So this, like 3, 1, is, one of these things here. It's one of these multiplications. All right? That takes place, that translates things here into things here. This translates things in pairs of reals into reals by taking its multiplication by this 1 by 2 matrix. So if we have something it's a column vector of 2 numbers and we multiply it by 1 minus 1, we'll get a single real out, right? And what's shown here is an attempt to.
Oh, I'm so sorry.
I didn't realize I clicked that button. I'm so sorry.
No worries. Is it what's shown here is an attempt to depict sort of what is mapped over these spaces in these maps between spaces. You notice these are very specific maps, right? These are very specific values for this. Very specific mappings from this vector space into that. In other words, these are the morphisms in the category of vector spaces, right? Right? These are the linear maps. Each of these is a linear map. So each of these translates, it goes to a stock of vector space that's associated with the vector space. Each of these morphisms turns into a morphism between vector spaces, which are linear maps. Are we good with this idea? Now, this is not yet an assignment of data to these things, right? This is saying where the data lives. This data point lives in pairs of reals. This data point lives in pairs of reals. This data point lives as a single real. And it's saying whatever you have for this, you get what you need to get what you have for this by translation between these in this way and between these in this way. But remember that because of functor compositions, because things commute over here, so poset, things commute here, these have to commute. So whatever we assign here has to be consistent with what we have here and here, given these linear maps. Are we good with this? So whatever number we're going to put down here, whatever stance we're going to take to put a number down, it has to be consistent with, it has to, play nicely with this number and this pair of numbers and this pair of numbers and this pair. So this is like a giant Sudoku puzzle, right? Like I need to have something here that plays nicely with here. It's like a crossword puzzle, right? Like what I put here impacts what I put here and what I have here. And all of these have to play nicely together. But if they play nicely together, we're going to have a single unique global section that will result. And so here's a unique global section. Here we have a particular value from that R squared we were talking about. Here we have a particular value from this R squared. Here we have -4, particular value from here, right? And you can do the math, right? So if this -6 -2 multiplied here by 1 and -1, so this is a column vector, this is a row vector. I'm thinking the row vector as here. It's actually a matrix. It's kind of a degenerate matrix, right? And if we multiply here, this is a matrix we apply to the left of this -6 -2. So we have 1 times -6 minus plus -1 times -2, in other words, +2, which is -4, right? And same thing here. We have this 2, 1, which is a matrix, and we're going to multiply on the left times this. We have 2 times -1, and then we further subtract or add 1 times -2, and we're going to get -4. right? And all these things play nicely. It's a consistent picture across the entire thing. Everything is accounted for neatly in its own box in this very nice way that harmonizes with everything. So this is what we'd like to have. This is going to give a consistent value for all of these points here, such that when we translate it into anything else, we get values consistent, right? So this is kind of like this is the solution to the puzzle. Everything fits in its place. Now, as Daniel Rosiak says and shows in the book, if you make a misstep and you assign, or you get data that just, it has some real problems with it, and we assign a value here, we may be able to get sort of local sections which align here, but we may be unable to get a value here, which makes this whole thing work. It's like we think this is the puzzle piece that goes here. It's not quite a perfect analogy. We put it in and it screws up everything else, our interpretation, so that we can't make this work, right? So this local assignment would make this having a global section attractable. There's no one value we can put here that will make this add up. And as Daniel Rosiak says, it's not always that stark. Like sometimes it may be that you can have one of two possible, the possibilities are either you have this, or you either need this or for one set of these things to work, this other one for this other set of things to work. It's not that there's no value whatsoever, you have no possibility of having this, but you have two discrete conflicting possibilities to make different sub areas of this work. There can be sheaves which have many possible assignments where it's non-specific. And I believe those will be called flabby sheaves because they kind of flop around and they're not, pinned down. They're just, there's too many possibilities. It's like, it's flabby. It's just sort of flops around. Okay.
That's why you need a harmonic cochain to ensure the global section exists, right?
That may be, I need to learn. You need a harmonic cochain.
Yeah,
that's really interesting. That's plausible. That seems.
Yeah, because in my understanding, harmonic cochain is those cochain make sheaves Laplacian.
Okay.
On the x equals to 0, it means the local inconsistency are 0.
Right.
It's the global
okay, so that's what harmonic cochain means. Okay, yeah. Then that's right. That's right. Because you need the cohomology to be equal to 0 in order for.
Which order of cohomology?
Well, you would need it for so 0 with cohomology is going to give you the global sections. But higher cohomologies will show you inconsistencies. Yeah. It was sort of data loops or something that where it doesn't add up at higher levels is my understanding. So you can sometimes get more information in a way that will make some of those go away, for example. Yeah.
You can tell things differently. You can tell the consistent things from different
perspectives. Yes, I think that's right. Okay. For cellular sheaves, morphisms between sheaves, I will just note, have this rather nice property that they're morphisms between functors. So just have natural transformations between the functors involved. So if we have a sheaf morphism and it assigns data to sigma and data to tau. And we have this mapping here that tells us how to go from this assignment of data, from this set of possibilities to this possibilities, right? And we could do it for G as well. All we need is, for a sheaf morphism, is natural, these are components of natural transformation that tell us how to go from the encodings here to the encodings here for F, the encodings for G, encodings for tau to the, from F to those for G, such that this commutes. So this is just a natural square. Category theorists sometimes call this the obvious naturality square, but it's the naturality square. There's a naturality square between functors. It's not obvious if you're just learning category theory, but this is the naturality square between functors. And the striking thing is, again, these are just functors. There's no like lots of extra conditions here. It's just we are dealing with functors here. But the functors do form a sheaf. This commutes. This has to commute. Okay. Although sheaf and you can formulate a sheaf isomorphism. Okay. I had some extra slides on sort of working towards cohomology, but I think I'll save those till next time. So I'm going to stop this.